Witness the power of human innovation as we build monumental hydroelectric dams and vital energy infrastructures, shaping a sustainable future. The Lynth Limmer pumped storage plant in Switzerland represents one of the most impressive examples of modern dam construction in a high alpine environment. Before construction began, the terrain was carefully excavated about 2 meters down to reach the solid rock foundation. Geologists examined, measured, and mapped the area precisely, filling cracks and fault zones with special concrete to ensure the dam's long-term stability. The dam wall itself consists of 68 individual concrete blocks, each 15 meters wide. To ensure precise alignment and stability, every second block was built first, allowing the sidewalls of these initial blocks to serve as formwork for the intermediate ones. The blocks interlock through specially designed recesses in their side surfaces, creating a solid and continuous structure. Concrete used for the wall construction was produced in an on-site batching plant, where various mixes could be automatically prepared depending on the section of the dam. From the silos, aggregates such as gravel were delivered to the concrete plant. The prepared concrete was then transported by dumpers to the placement site, where mobile tower cranes lifted heavy 17-ton buckets into the formwork. Because of the tremendous weight, cranes had to be positioned very close to each block. Each block was constructed in 3-meter-high concreting stages, with the formwork for the lowest section carefully aligned. Within these stages, concrete was poured in 50-centimeter thick layers. As the concrete begins to harden immediately, it had to be spread and compacted quickly using vibrators to avoid air pockets. The next layer had to be placed within 2 hours to ensure a perfect bond between layers. Pouring one large stage could take up to 12 hours of continuous work. To control temperature and prevent cracking, cooling pipes were installed at the base of the massive lower sections. Once each stage was completed, its surface was roughened with high-pressure water to ensure a strong connection to the next layer. A gallery running through the entire dam allows for future inspections and maintenance work. The tallest blocks reach the height of a 10-story building, and the upper sections near the dam crest were extremely narrow, leaving little space for machinery. Crane operators had to rely on radio instructions since they could not directly see the heavy concrete buckets. Located at an altitude of 500 meters, the construction site faced severe weather challenges. Fog, cold, and unpredictable snow made progress difficult, especially as autumn approached. Because the window for construction was short, work continued 24 hours a day, with lower blocks being concreted, while climbing formwork was prepared for the upper ones. Thanks to favorable weather conditions in 2013, remarkable progress was achieved between spring and autumn. By November, the last stages of the season were poured against a backdrop of early snow. The remaining sections were completed in 2014, and by 2015, the dam crest was finished, making the Lynth Dam the longest of its kind in Switzerland. Deriner Dam, located in Artvin, northeastern Turkey, is an impressive structure that once held the title of the highest dam in the country. With a foundation height of 249 meters, it ranks as Turkey's second highest dam today, following the completion of the 275-meter-tall Yusufeli Dam in the same region. When it was built, Deriner Dam was not only the tallest in Turkey, but also ranked as the sixth highest dam in the world. Its majestic appearance and engineering excellence make it a remarkable landmark of modern Turkish infrastructure. Constructed across the Koru River, the dam serves multiple purposes, including hydroelectric power generation, flood control, and water storage. The surrounding mountainous landscape enhances its breathtaking view, making it one of the most iconic engineering achievements in Turkey. Deriner Dam remains a symbol of technological progress and human ingenuity, demonstrating Turkey's capability in large-scale hydropower and civil engineering projects. The transportation of construction machinery for the Yusufeli Dam project was an impressive engineering operation carried out in the Artvin Mountains of Turkey. Due to the steep and narrow terrain, many heavy machinery such as excavators, loaders, and trucks could not be transported by conventional roads. Therefore, cranes and steel wire ropes were used to lift and transport the equipment to high and difficult-to-reach areas. Each machine was carefully secured, lifted by strong steel cables, and positioned precisely at the construction sites. This aerial transportation ensured that work could continue efficiently, even in difficult geographical conditions. The operation required excellent coordination between the pilots, ground crew, and engineers to ensure safety and accuracy. Thanks to these innovative logistical solutions, the machinery arrived at the dam site on time, contributing significantly to the successful completion of the Yusufeli Dam, one of Turkey's most ambitious hydroelectric projects. The Yusufeli Dam, built by DSI Genel Müdürlüğü, is one of the most remarkable hydroelectric projects in Turkey. Located on the Koru River in Artvin province, the dam reaches a height of 275 meters, making it the highest dam in Turkey and among the tallest arch dams in the world. Its construction involved advanced engineering and careful geological planning to withstand immense water pressure. The project began with large-scale excavation and the construction of diversion tunnels to control the river flow. Then, concrete placement was carried out in successive layers using precision-controlled equipment. The dam's double curvature arch structure allows it to transfer water pressure effectively to the abutments on both sides of the valley. The integration of modern machinery, including tower cranes, concrete batching systems, and automated monitoring instruments, ensured safety and efficiency throughout the process. Thousands of skilled workers, engineers, and technicians collaborated under strict safety and environmental standards. Upon completion, the Yusufeli Dam will generate 558 megawatts of electricity, significantly contributing to Turkey's renewable energy capacity. Beyond power production, it also provides flood control and irrigation benefits, demonstrating how advanced technology and human expertise can transform challenging mountain terrain into a sustainable energy source. The Baihetan Hydropower Station, located on the Jinsha River in southwest China, is one of the most impressive examples of modern dam engineering and a symbol of China's technological achievement. Rising 289 meters high, it is the second tallest dam in the world and a crucial part of China's effort to expand renewable energy production. The project was undertaken by China Three Gorges Corporation, the same company that built the world-famous Three Gorges Dam. Construction required an extraordinary level of precision, coordination, and innovation to overcome the difficult geological conditions of the deep mountain valley. The process began with the diversion of the Jinsha River through massive tunnels, allowing the dry construction of the main dam body. Advanced concrete technology was used to pour over 8 million cubic meters of specially designed low-heat concrete to prevent cracking in the massive structure. The placement was fully automated, supported by GPS-controlled cranes and intelligent monitoring systems that maintained uniform quality. At the heart of the project are 16 hydroelectric generating units, each with a capacity of 1 million kilowatts, the largest in the world. The construction of the Baihetan Dam represents the seamless cooperation between human intelligence and machine precision. Thousands of engineers, technicians, and workers operated around the clock in perfect synchronization, supported by fleets of heavy machinery such as cable cranes, concrete transporters, and robotic inspection devices. Every phase, from excavation to turbine installation, demonstrated remarkable coordination and safety discipline. When fully operational, Baihetan will produce more than 62 billion kilowatt-hours of clean electricity annually, reducing carbon emissions and powering millions of homes. Beyond energy generation, the dam provides benefits such as flood control and water management for the surrounding regions. The success of Baihetan reflects China's capability to combine cutting-edge engineering, environmental responsibility, and collective human effort to create one of the world's most magnificent hydroelectric achievements. The Breakwater construction project is a major EPCC engineering, procurement, construction, and commissioning initiative designed to protect coastal infrastructure and create safe harbor conditions for vessels. The project includes the construction of breakwaters, quay walls, berths, jetties, navigation beacons, and auxiliary facilities that together form a complete maritime protection and docking system. Its primary objective is to reduce wave energy, prevent coastal erosion, and provide a calm water area for port operations. The construction of the breakwater is the central component of the project. It begins with seabed preparation, including dredging and leveling to provide a stable foundation. Layers of filter materials such as sand and crushed stone are placed to prevent soil migration. After that, heavy core rocks are deposited to form the inner mound of the structure. The breakwater's outer layers are built using armor stones and specially designed concrete units like tetrapods or X-blocks, which interlock to dissipate wave energy effectively. Each unit is precisely positioned using cranes and GPS guidance to ensure structural stability. Quay walls and berths are constructed alongside the breakwater to accommodate ships and facilitate cargo handling. Reinforced concrete structures are used for high durability and resistance to marine corrosion. The jetties extend from the shoreline into the sea, providing access for vessels and maintenance operations. Navigation beacons are also installed at strategic points to guide ships safely through the entrance channel. Throughout the construction process, strict quality control and environmental management measures are applied. Materials are sourced and tested according to international standards, and marine ecosystems are monitored to minimize ecological impacts. Modern construction equipment such as floating cranes, barges, and pile-driving rigs are employed to ensure efficiency and precision. Upon completion, the breakwater system will serve as a vital maritime infrastructure that enhances port safety and operational capacity. It will protect the harbor from strong waves and storm surges, enabling year-round shipping activities. The project not only supports regional economic growth through improved logistics and trade, but also contributes to the sustainable development of coastal areas. In summary, this EPCC breakwater project demonstrates advanced engineering and environmental responsibility, providing a robust and lasting solution for coastal protection and port operation. The Valamon jacket installation was a landmark offshore engineering project executed by Hydropower Fabrication Group. From the initial FEED study to final offshore installation, the process showcased the complexity and precision required for such a massive offshore structure. Fabrication of the jacket officially began on June 6th with the symbolic first steel cut. Within just 50 weeks, Hydropower completed the structure, representing over 350 man-years of combined effort. The final product stands an impressive 160 meters tall, has a footprint of 45 by 45 meters at the base, and measures 25 by 35 meters at the top. It is the largest and heaviest jacket Hydropower has ever constructed, and the heaviest ever installed using a crane vessel reaching the maximum lifting capacity of the Thialf. The fabrication process involved several key phases. One of the first major assembly steps was the third roll-up, followed by the welding and installation of the top part of row 5. J-tubes and risers, used to guide pipelines and cables, were fabricated and installed in two main phases. First, the bottom parts of the J-tubes, then the upper connections. Structural bracing continued with the installation of crossbeams in row A, which helped improve rigidity and load distribution across the frame. After fabrication was complete, Extensive preparations were made for the loadout procedure. This required detailed planning to ensure structural stability and proper alignment when moving the jacket from the construction yard to the transport barge. Once secured, the Valamon jacket was rolled out onto the barge using SPMTs. The sail away occurred 3 days ahead of schedule, a significant milestone for the project team. Transport to the offshore installation site took approximately 3 days. Upon arrival, the offshore phase began, which would last between 2 and 2.5 weeks. The massive structure was installed using the Thialf, one of the world's most powerful crane vessels, requiring exact coordination of lifting, positioning, and seafloor securing operations. One of the major engineering challenges during this project was controlling the overall weight of the jacket. Due to the size and lifting limits of the installation vessel, every ton mattered. Additionally, since the Valamon platform is positioned within an active shipping lane, the jacket had to be designed to resist potential boat impact. This resulted in several design modifications and reinforced structures to ensure long-term safety and durability. Project manager C. Spons emphasized the pride the team had in delivering such a complex structure on time, noting that the project brought together a large group of people who worked tirelessly over 2 years. The Valamon jacket stands today as one of the safest offshore structures in the North Sea, built to the highest engineering standards. It is not only a demonstration of Heerema's technical capabilities, but also a testament to successful planning, collaboration, and execution in offshore construction. The Amur gas processing plant construction project, managed by JSCNI PIGAS for Gazprom Pereirabotka Blagoveshchensk LLC, reached an overall progress of 75.1% by April 2021. Commissioning activities were underway at Startup Complex 1. The plant has been successfully connected to the Power of Siberia main gas pipeline, with all 4 tie-ins for the commercial and feed gas pipelines completed. Feed gas is already being supplied to the dehydration and treatment unit of Process Line 1, where equipment installation and setup are actively progressing. At the booster compressor stations, Ladoga Gas Pumping Unit 1 was fully prepared for gas reception and hot start, while alignment and cold start procedures were ongoing for GPU 2. Simultaneously, preparation for receiving dehydrated gas was being finalized at the ethane, NGL, and nitrogen-helium mix units. Functional testing of equipment was carried out across Process Line 1 to ensure operational reliability. The first 3 spherical storage tanks in the product and feed area were ready for operation. At the nitrogen and air station, air supply to the mains had begun, and preparations for nitrogen delivery were in progress. Construction and installation work at the water treatment facilities were completed, followed by the commissioning phase of the water treatment plant. When fully operational, the Amur GPP will be one of the largest gas processing plants in the world, with a total capacity of 42 billion cubic meters of natural gas per year. The facility will comprise 6 process lines, with the first 2 scheduled for commissioning within the year. The plant's main products will include purified methane, ethane, propane, butane, pentane hexane fractions, natural gas liquids, and helium, marking a major milestone in Gazprom's gas processing and export infrastructure. The Taylor TXEC-207-8 efficiently handles empty containers using a 63-foot Ultra VU telescopic mast and a side-mounted ISO container attachment with rear twist locks. In the video, the operator grips, lifts, and stacks containers up to 8 high, with plus or minus 24-inch side shift for precise alignment. Powered by a Cummins QSB 6.7L 225 HP Tier 4 final engine and Dana TC32 power shift transmission, the machine moves smoothly in tight spaces. It features a 180-inch wheelbase, Axletech planetary drive axle, and heavy-duty pneumatic tires for stability. The elevated cab includes a multifunction joystick, 7-inch touchscreen, and wide-angle mirrors, offering excellent visibility and control. LED work lights and twist-lock signal lights ensure safety. The TXEC-207-8's robust chassis, advanced hydraulics, and intuitive controls make it ideal for high-volume container yards. The assembly process of the Terex Demag CC6800 crawler crane begins with preparing a compacted and leveled ground surface to support the crane's total weight and counterweight configuration. The undercarriage modules, equipped with dual crawler tracks, are positioned using transporters or smaller mobile cranes. These tracks provide the crane with both mobility and low ground pressure. The car body is then mounted onto the undercarriage, followed by the installation of the slewing ring and rotating superstructure. The backmast, which provides additional leverage and counterbalancing capability, is attached to the rear section of the superstructure. Counterweight slabs, each weighing several tons, are loaded onto the tray using auxiliary cranes and secured using locking mechanisms. The central ballast is mounted first, followed by the superstructure counterweight in a symmetrical layout to ensure balance during lifting operations. The main boom, composed of lattice sections, is assembled on the ground using pin connections. Hydraulic or strand jacking systems are then used to raise the boom to its working angle. The superlift mast and tray are connected if the lifting plan requires extended reach or capacity. Once the configuration is complete, typically including main boom, backmast, counterweights, and superlift, if required, the crane undergoes functional testing. Control systems, including load moment indicators and boom angle sensors, are calibrated. This assembly process ensures structural integrity, load stability, and readiness for lifting critical oil and gas infrastructure components. The Liebherr LTM 1500-8.1 is a powerful all-terrain mobile crane with an impressive maximum lifting capacity of 500 tons. The assembly process of this crane is shown in detail. Upon arrival at the site, the crane is positioned on stable ground, and the 8-axle chassis is leveled using hydraulic outriggers. The counterweight slabs are then delivered by transport trucks and carefully mounted on the superstructure using the crane's auxiliary hoist system. Next, the telescopic main boom, which can extend from 16.5 to 84 meters, is attached and secured. The video highlights the setup of the Y-guying system, which enhances lifting capacity by providing extra boom stability during heavy lifts. Additional extensions such as the lattice jib can be installed, allowing the crane to reach a maximum lifting height of 148 meters when combined with a 91-meter luffing jib. The LTM 1500-8. One's all-wheel steering provides excellent maneuverability, enabling it to move easily across rough terrain or travel independently on public roads at speeds up to 85 kilometers per hour. Thanks to its modular design, setup is efficient and quick, making it ideal for both short-term and long-term projects. This versatile machine is widely used in industrial and civil construction, infrastructure projects, and energy installations, including wind turbine erection and other heavy lifting operations.